Okay, we want to look at another example. This would be, and we're just going to go ahead and use 1 over x as an example. Okay? Now this would be the interval from 1 to infinity of 1 over x dx. Okay? And that would correspond intuitively to all the area from x equals 1 out to forever. Okay? Okay, well, we can't do the area from 1 to forever, right? So we're going to do the area from 1 to c. Okay? This area is the integral from 1 to c of 1 over x dx, which is easily calculated to be the natural log of c. C is positive, so I don't have to put the absolute value signs on it, minus the natural log of 1, which of course is just the natural log of c. Okay? Okay? So, the integral from 1 to infinity of 1 over x dx is the limit as c approaches infinity of the integral from 1 to c of 1 over x dx. In other words, we can't plug infinity in. The natural log of infinity is not defined, because infinity is not a number. The natural log is only defined for numbers. So we let c approach infinity and integrate from 1 to c. Okay, well that's the limit as c approaches infinity of the natural log of c. Okay? Now what's that limit? Well, you have to understand the natural log function. Okay? Remember, you can write a table for the natural log of function, for natural log function, for natural log of x is kind of mixed up there. Okay? So if x is, now we want x to be big numbers, right? So let's just let x be, 100, 1,000. And actually, you know what I want x to be e to the 100, e to the 1,000, e to the 10,000, and so forth. Okay? What's the natural log of e to the 100? Well, remember on the graph of e to the x, you have a line that has 100 e to the 100, right? Just like you had 2 e to the 2. Okay?
The natural log of x would be 100?
Yeah, exactly. Very good. And 1,000 and 10,000. Is there any limit to how big your power of e can get? You can still, it's still a number. I mean, this is an unimaginably large number. It's greater than, way greater than the number of particles in the universe as we conceive of the universe, and it's pretty big with a lot of particles. You only get about 10 to the 80 some particles in the whole universe. Well, e cubed is bigger than 10. So e to the 10,000 is bigger than 10,000 thirds. So that's bigger than 10 to the 3,000th power, and 10 to the 80th power is on the order of the number of particles in the known universe. It's 80 something, 86 maybe, I think. Last time I looked, last time I counted them, I think that's what it was. Okay? You ever count them? Okay, well, you rely on estimates. You know, how many galaxies, how many stars in a galaxy, how many atoms in the average star, how many particles associated with each atom, okay? And then you got photons produced by the stars and stuff. So, yeah, a lot of particles, neutrinos and all that stuff. Okay, anyhow, you got a lot of particles. I mean, the Earth is pretty big, but, you know, compared to the universe, it's not even, it doesn't even count. A lot of particles in the Earth. Okay, so the whole point is that the limit as x goes to infinity of the natural log of x we say is infinity. Okay? There's no limit to how big they get. So any number that you want to say, the natural log, you can find an x that's the natural log is bigger. Okay? I'm not going to ask you to do any detailed analysis of that sort of thing, but you want to kind of have that idea in case you run into it later, and because it makes more sense out of everything that we're doing. So the more sense you can make out of it, the better you'll understand it. So bottom line, when you have an integral like this, you do the limit as you do the integral to c. Okay? Make sense? And you get what you get. Now another one. Okay, integral from 0 to 1, 1 to the square root of x dx. What's that going to be? I'm going to use epsilon. You can use c if you really hate epsilon that badly. It's kind of a neat little thing to make. Okay? And I didn't say that you hate epsilon. I just said it turns out that you hate epsilon because you haven't expressed any positive or negative except you wondered what it was, right? Now that you know what it was, you might decide you love it, and if you don't, I don't mind. Okay. Well, you just automatically, if you got something where this thing, if one of your limits makes this undefined, you have to do this, right? So that's a limit as epsilon approaches 0 of what? Antiderivative of square root of x is, of 1 over the square root of x is 2 square root of x, isn't it? Okay? Well, we split that into the upper limit and the lower limit and take the limit as epsilon goes to 0 of both. 2 doesn't change. So we get 2. And what happens to 2 square root of epsilon as epsilon approaches 0?
It's just approaching infinity. It is infinity, right?
Well, I don't know. What happens to a small number when you take its square root? Does it get big?
No, it gets smaller.
Uh-huh.
Yeah.
And if the number approaches 0, what happens to its square root?
It just gets really, really small.
Yeah, well, it approaches 0. Okay? Okay? Well, that means the limit of this area as you go on forever for this function, the 1 over square root of x, the graph's going to look a whole lot like this. It's not going to it's not going to be as high because the square root of x is bigger than x, right? It's smaller than x. Okay, okay, never mind. You're looking at the integral from 0 to 1, okay? 1 over the square root of x is going to be smaller than 1 over x in a way that makes this finite. So if you have the 1 over square root of x curve and you take integrals from close to 0 out to 1, and keep getting closer and closer and closer and closer to 0, even though you've got a vertical asymptote, as x approaches 0, this approaches infinity, right? You still end up with a finite area. Just like here, even though you've got an infinitely long region, it still has a finite area. Sorry, this one doesn't. But if it was 1 over x squared, it would. Okay? So again, you can easily prove integral from 1 to infinity of 1 over x squared dx is defined to be the limit as c approaches infinity of the integral from 1 to c of 1 over x squared dx, which equals the limit as c approaches infinity of, well, the antiderivative is negative 1 over x, right? So it's going to be negative 1 over c minus negative 1 over 1, which equals the limit as c approaches infinity of 1 over c minus the limit as c approaches infinity of 1, of negative 1, sorry, because that's negative 1, it's always going to be. Well, if you divide 1 by bigger and bigger numbers, what do you get? You get smaller and smaller numbers, right? And if there's no limit to how big the numbers get, there's no limit to how small the reciprocal is going to be. So that limit is 0. So if I do the same picture for 1 over x squared, it has a finite limit. Okay? Now there's more to it, and you can see through the examples. One thing you've got to watch for, and we don't have time to go over it in any detail, and I don't have another board handy, so I'll kind of do it in a different color here. What if you wanted the integral from 1 to 2 of 1 over x minus 1 times x minus 2? Well, if x is 1, 1 over x minus 1 is going to approach 0, right? So this thing is going to approach infinity. And as x approaches 2, it's going to be the same thing, okay? And actually it approaches negative infinity at this limit and positive infinity at this limit, right? So you can say that you can split this from 1 to, I want to use c, but they're using c, okay? From 1 to b plus the integral from b to 2 okay? And the problem here is you have an asymptote at x equals 1, okay? And you have an asymptote at x equals 2. And you can't deal with both of them with the same expression. So we split this where b is somewhere between 1 and 2. And now we can say, well, this one is then going to be the limit as c approaches 1 of the integral from c to b of 1 over this times this dx. And these two parentheses contain the same expression, right? And then it's going to be plus the limit as, I can still use c because this is a completely different limit and this is a completely different c. Okay? If you wanted to use a different number, you could. You could use anything you want, but it's then from b to 2. And now you're using c only at one limit in this integral and only at one limit in this integral, right? I'm sorry, D. Yeah. Okay? And it's b to c, not b to 2. Okay? That make sense? They're examples. I'll show you. If you understand the basic idea that we've gone over here, you should be okay.